Hi everyone! So in this video, we're going to be learning some of the tools that we'll need to talk about the fundamental theorem of calculus. So the fundamental theorem of calculus is basically a couple of different facts that are really important. We're not going to get to those until the next couple of videos, but there's basically just a new type of function that I need to introduce so that you can be more comfortable once we get to the fundamental theorem of calculus. So that's what this video is going to be about. So the new type of function that we're going to learn about is something that's called an area function. So we'll see that an area function is basically just a way of, we know how integrals are a way of calculating areas, right? And so basically an area function is just a way of turning that idea into a function. So I'll show you what I mean by that in a moment. So an area function is a function of the form, and this will probably look a little confusing at first, but I think once I explain it and we get into some more examples, it will become a little clearer what's going on here. Okay, so what's going on here? Basically, we have an integral, right? So the integral, we've learned about that in previous videos. That's calculating the area, right? The area between two numbers bounded by a function and the x-axis. So what is the input in this function? Well, it's the top bound, right? So maybe I'll even emphasize that with a different color here. So you're plugging in different numbers for x, and then you're calculating to find the output. You're calculating the integral from a, which is itself a fixed number, to different numbers x. So maybe let me write that down. So in an area function, the input is the upper bound. So it's basically the second number of where you're taking the integral from. So the input is the upper bound of the integral. And then the output is the resulting area. And remember, when I say area, I'm kind of stretching the meaning of the word area because when we're taking an integral, the area could end up being positive or negative. So again, we'll get into an example in a second that I think will clarify everything, but there's one other thing I just want to point out here that maybe seems a little strange to you. So you might be wondering, like, why do we have an x here and then a t here? And it's because these two things represent two different things. So the x is just the variable of this area function, or the input variable of this area function. So x represents the bound changing. So for example, if you plugged in 1 for x, you would be doing the integral from whatever a is to 1 of your function. Or if you plug in 2 for x, you would be doing the integral from a to 2 of your function. So x is changing. X, we're always plugging in different numbers for x, and that will give us different outputs. T, on the other hand, that's just the variable of our function that we're integrating. So this is something that maybe I should have emphasized. I don't think I really mentioned this, but when you're doing an integral, it doesn't matter what variable you actually use. So I'm just going to kind of write this as a side note. For example, if you're taking, let's say, the integral from 1 to 2 of x squared dx, that means the area bounded by the function f of x equals x squared and the x-axis between 1 and 2. That's the same exact thing as if you were to say the integral from 1 to 2 of t squared dt. And that's the exact same thing as if you were to say the integral from 1 to 2 of y squared dy. And that's the exact same thing as if you said the integral from 1 to 2 of w squared dw. So it really doesn't matter what variable you're using inside your integral. That's just kind of a placeholder. And as long as the variable here matches the variable here, you're all good. So, so the variable t here is just kind of a placeholder variable. It's just representing your function. Whereas the variable x has a very specific meaning. It's intended to mean like specifically the upper bound. And let me just apologize. I'm not sure if you'll be able to hear this, but there are definitely some fireworks going off in my neighborhood. So hopefully you won't be able to hear them on the video, but if you do, I hope they won't be too distracting. So one other thing I guess I should quickly mention is that sometimes, so I'm using capital A of x. Another common letter to use for an area function would be capital F of x. So we might use that as well. Okay, so let's look at an example. So let's say that this is our function. We're going to call this function f of t. And we're going to make an area function, and our area function is going to be a of x is equal to the integral from 0 to x of f of t dt. So first thing I want to do is just evaluate a few points on this function, right? Like with any function, how do you work with the function? You plug in values and see what you get as your outputs. So let's try to find, let's do a of 2. Let's do a of, let's say a of 4. And actually, I'm going to use some different colors for this because it will help us be able to make sense of what I'm going to draw in the picture. Let's do a of 4, and then maybe let's do a of 14. So let's see, sorry, just picking out my color. I'll do orange for that. Okay, so what does it mean to evaluate a of 2? Well, just like with any function, all it means is that you're taking 2 and you're plugging it in for x. So we're going to be doing the integral from 0 to 2 of f of t dt. So what does that mean? Well, that just means the area bounded by x equals 0 and x equals 2 between the x-axis, or I guess maybe I should call it the t-axis because that's the variable we're using for our function, and the graph. So basically we're looking at this area here. So what is that area equal to? Well, it's 1/4 of a circle, right? So a circle with a radius of 2 would have an area of pi r squared, which would be 4 pi. But we're looking at 1/4 of the circle, so our area is going to be 4 pi over 4, which is pi. So a of 2 is equal to pi. So our input is 2 and our output is pi. Okay, so let me just actually scooch these down. I feel like they're a little close. Okay, so a of 4 would now be doing the same thing, but now we're doing the integral from 0 to 4 of f of t dt. So how would we find that? Well, now we have an area that's going to start with this part over here, but then it's also going to include the stuff down here. And so remember, when we have parts of the graph that are under the x-axis, we need to count them as negative. So what is this area going to look like? Well, it's going to be pi, right? That was the first part in green. But then from that, we have to subtract the area of this purple triangle. So what's the area of this purple triangle? Well, it's base times height over 2. So the base is 2, the height is also 2. So that would be, 2 times 2 over 2. And that is going to simplify to just being pi minus 2. So when you plug in 4, your output is pi minus 2. I guess I still didn't give us enough space. All right, last one would be now the integral from 0 to 14, because now we're plugging in 14 as that upper bound. So now we're going to be adding up, again, this initial quarter circle. Then from that, we're going to be subtracting this triangle. And then to that, we're going to be adding this half circle. And so the total area we're going to get is going to be, so we had pi for the circle. Then for this triangle, well, we could kind of add the purple triangle that we already drew to this other triangle, but we might as well just do the whole thing at once. So the base of this orange triangle would be 6, right? 1, 2, 3, 4, 5, 6. And then the height is 2. So we would have base times height over 2. So 6 times 2 over 2. and we're subtracting it because it lies below the t-axis. And then we're going to add this last area, this semicircle, and so that's going to be, so the radius of that circle is 3, right? So we want to do pi times the radius squared, so that's 9 pi, but then we want to divide that by 2. And so altogether, this gives us pi minus 6 plus 9 pi over 2. And you could make a common denominator or something. I'm not going to worry about that for now. Really, the main thing I just want you to understand is basically what does it mean to evaluate this area function? It just means you're plugging in different numbers for your top bound. One other thing I just want to point out is that in this area function, we have the lower bound being 0. But it doesn't have to be. So notice here I just put a letter A. It could have started at 1, and then we would be doing the area from 1 to 2 and 1 to 4 and 1 to 14. We could have set this lower number as 2, and then we would be doing the area from 2 to 2 and 2 to 4 and 2 to 14, etc. So that lower bound is fixed, but it can be fixed at whatever it's being defined as. Okay, there's one other thing I want to talk about with this specific example, which is the idea of finding local maxima and minima of this area function. So, that might seem a little strange, and actually I'm going to copy and paste this so that I can go down here. It might sound a little strange that we're talking about local maxima and minima, but remember, an area function is just a function. So we can do anything, anything that you can do with a typical function, you can do it with an area function. So the question we want to answer is we want to find at which t values, or I guess, sorry, at which x values, because x is our input here, do the local, maxima and minima of a of x occur. So first thing I just want to remind you is, what is a local maxima or minima? So maybe I'll go down here and just kind of do a quick reminder. So basically, the only thing we really need to know in order to answer this question is that a local max looks like a peak, a hill in a graph, and a local min looks like a valley. And it's easy to get confused here. Remember, we're not looking for the local maxes and mins of this function that's graphed. We're looking for the local maxes and mins of the area function. So let me say it this way. A function f of x has a local max at x equals c if f of c is higher than the points around it. I'll just say nearby. Right? So when you have a local max, if you think about what a graph looks like, it's like a peak or a hill in your graph. And so that basically means that you're achieving a y value that is higher than the other y values around it. It doesn't have to be the very highest, but it's higher than the ones nearby. And then similarly, f of x has a local min at x equals c if when you plug that number in, you get a result that is lower than other points nearby. So that would give you, it doesn't have to be the overall lowest point, but it would kind of give you that valley shape if you have a part of the graph that's lower than the other points nearby. And so that's what we're going to keep in mind when we answer this question. And so again, it's, I think, really, really easy to get confused and say, oh, local min, local max, but that's not true in this case, because we're not looking for the local maxima and minima of this function that's graphed here. We're looking for the local maxima and minima of the area function. So what I want to do is we're going to kind of roughly sketch, and I don't want you to think that we're doing this precisely at all, because we're not, but I want to roughly sketch what the area function looks like as we go from left to right here, because I think that's what will help us see when is it, where are we going to have these peaks or valleys happening. So let's say that you're taking the area function from, you're plugging in 1 or 2, right? So if you're plugging in 1, so a of 1, that would be this area here, right? So that would be a positive area. And then if you keep going and do the area up until 2, that's still positive, right? And so that means that our area function is going to be, and again, this is not really accurate to exactly what it would look like, but it's increasing, right? The area function is going up from 0 to 2 because you're adding more area. You're increasing the area. However, as soon as we hit 2, now all of a sudden we're adding in some negative area, right? And we're adding negative area all the way until we get to 8. And so that means that the area is going to start going down. And again, I don't know exactly what it looks like, but I know that it's going down, right? The area is starting to decrease because at first we were only adding in positive area, but now we've started counteracting it with negative area. So slowly that initial area that we built up is going to go down and down and down. And eventually, I'm not sure, but it looks to me like it will become negative. It looks to me like this triangle will counteract the quarter circle. Now when we hit 8, well, after 8, now we're adding in more positive area. And so what's going to happen to this area function? Well, it's going to start increasing again. And I want to, again, just reiterate, the area function would not actually be linear like this. This is not exactly what it would look like. I'm just doing this to give a sense of, is it increasing or decreasing? So the area function is increasing as long as you're adding in more positive area. It starts decreasing as soon as you're starting to add in that negative area, and then it starts increasing again when you start adding in more positive area. So this orange line is meant to be, again, a very rough sketch of a of x. So now that we have this rough sketch, now we can actually answer the question. So what is the first place where we see, or where do we see a peak in the graph? Well, at x is equal to 2. So we have a local max at x is equal to 2. And so why is that? Well, it's because that's the place where we kind of switch from adding positive area in to then counteracting it with negative area. So even without drawing this orange graph, you can kind of see, you should be able to see how it goes from, adding in more area to then subtracting it. And that's when it kind of stops going up, right? And it starts going down. And so that's what gives it that, that hill or peak shape. So where's our local min? Our local min is at x is equal to 8. And that's because, we can see in this graph, it looks like a valley, but why does that happen? It's because x equals 8 is exactly when we start adding in more positive area. So that's when, we have the graph going down and down and down because we're adding in more and more negative area. But once we hit x equals 8, the area we're adding in is now positive again. And so that reverses the trend. And as soon as you reverse the trend from decreasing to increasing, that's what gives us this local min. So just to be clear, we don't know, or I'm not telling you here what the actual value is of the local max or min. You would have to get a little bit more specific. It wouldn't actually be that hard, right? You basically would just need to evaluate a of 2, which we actually already did, right? So a of 2 is equal to pi. So pi would be the local max, and then the local min, you would evaluate a of 8. So just like with any function, you have the x value where the local max or min occurs, and if you want the actual value of the local max or min, that's where you need to plug it into the function. Okay, so that's area functions. I want to now do a couple of examples, and this is going to really start to help us to understand the fundamental theorem of calculus. So we're going to do a couple of examples of specific area functions, and we're going to start by doing something similar to what we did in the last example, where we're just evaluating like a of 1, a of 2. But then we're going to try to find a way to write down a general formula for a of x. And we're going to do that for a couple of different functions. And then in tomorrow's video, we'll see like why that's significant. So I want to just quickly show you on Desmos. I built these up on Desmos in a way that I think might even make understanding the area functions a little easier. So if you look at this picture here, I set this up so that we have this kind of slider. So if you are, so here's the function f of t is equal to 3, right? It's a horizontal line at 3. And then so in this case, our area function, and I guess I should write that down. So here our area function is a of x is equal to the integral from 0 to x of 3 dt, because our function is just a constant, it's 3. So one way that you can think of this area function as working is this idea of a slider. So you're taking x and you're varying its value, right? You could take the integral from 0 to 0 of the function, that would just be 0, right? Remember, if you take an integral from a number to itself, it's just 0. And then if you do the integral from 0 to 1, that would be a of 1. And then the integral from 0 to 2 would be a of 2. And the integral from 0 to 3 would be a of 3. So you're really varying, as you vary x, you can think of that as sliding along this, this shaded area, the shaded region, and finding its area. Okay, so let's look at this example. So let's say that we wanted to evaluate a of, sorry, pen issues, stop. Let's say we wanted to evaluate a of 1. So this is actually easier than the last one we did, right? So a of 1 would just be the area from 0 to 1. So a of 1 would be the integral from 0 to 1 of 3 dt. And just by looking at this picture, we can see that that's 3, right? Because we'd have a base of 1 and a height of 3. What about a of 2? So how would we find a of 2? Well, that would now be the area from 0 to 2. So that would be the integral from 0 to 2 of 3 dt. And we can see from the picture that that area is equal to 6. So simple enough to actually just evaluate point-wise. But now I want to do something that is actually in this case not too tricky, but a little trickier, which is we want to figure out what's a general formula for a of x. So can we find a general formula for a of x? So what do I mean by that? I basically mean we want a formula that will tell us what is the area of the rectangle from 0 to x. So looking at this picture here, this is kind of a generic example, right? So we don't need to worry about exactly what x is. We're just thinking of this whole distance as being x. So what would the area of this rectangle be if the base is any number x and the height is 3? It would be 3x, right? So a of x is going to be the area of, I'll say it this way, the area of, I'll say the rectangle with a base of x and a height of 3. And so what would that area be? It's just going to be 3 times x. So I want to kind of write all this down, like the actual function, and then what we got as our answer, because in the next video, we're going to be kind of coming back to this example as well as the next one and kind of seeing something interesting that's happening. So just to kind of put it all in one place, if our original function was a of x is the integral from 0 to x of 3 dt, we found that a of x was also the same as just 3x. So you could write it kind of in the fancy way with the integral, or you could just say, hey, the area is going to be 3 times x. So again, I know I'm being a little mysterious, but in the next video, we'll see like why this is significant or interesting. Okay, so let's look at this next example. And this one's a little bit trickier. But again, we have this situation where we have an area function where we are picturing x as being the right endpoint. So we're kind of sliding this second point along and seeing what is the area of this resulting shaded region. So in this case, our function is h of t is equal to t plus 1. So in this case, the area function is a of x is equal to the integral from 0 to x of t plus 1 dt. So this one's going to be a little trickier just in terms of the geometry, but I want to evaluate again a of 1 and a of 2, and then after we do those, we'll see if we can come up with a general formula for a of x. So what would a of 1 be equal to? So that would be this area here, right? The area from 0 to 1. So how could we find this area? Well, there's a variety of ways, but I think maybe the easiest way would be to think of it as a square plus a triangle. You could also do it as a trapezoid. So if you remember the area formula for a trapezoid, you could do it like that. But I think most people are probably more comfortable with squares and triangles. So the square part, so this part, has an area of 1. And then the triangle part has an area of 1/2. I mean, we can just see that by looking at it, right? It's half a box. So 1 plus 1/2 is equal to 3/2. Okay, what about a of 2? So a of 2 is going to be now this whole area. So what is this area going to be? Well, now again, we can do a rectangle. So we can add up this bottom part as our rectangle. So that would be 2. And then this triangle is going to be base times height over 2. So that's 2 times 2 over 2. The area of this triangle part is 2. And so all together, we have 2 plus 2. So we have 4. Okay, so let's try to think of now how we could come up with a general formula for a of x. So let's just look at this kind of sample picture that we have drawn here. So in this sample picture, we just have x at some random point between 4 and 5. Let's not worry about what the actual number is, but let's think about how we could, for any x, calculate the area of, let's do the rectangle and then the triangle separately. So what's the area of this rectangle? Well, that's going to be x times 1, right? So the rectangle part of the area is going to be a base of x and a height of 1, which gives you an area of x. And then what about this triangular part? So this is the slightly trickier part. So if we look at this triangle, so we need to figure out what the base and the height are, and then we can divide that by 2. So the base is again going to be equal to x, right? Because that's we can just see that that is how long the base is. So what is the height going to be? Well, there's a couple of different ways to see it. One is just to see that this is an isosceles right triangle, right? So if you look at these angles, these are both 45-degree angles. And so that means that whatever the length of the horizontal side is, the vertical side has the same length. So it's also going to be x. Another way of thinking about it is that because this function is h of t is equal to t plus 1, basically, let me think how I want to say that. Like if you look at, for example, if you go to an x value of 2 and draw a triangle like this, notice that the y value is 3, but that's just because you have this bottom part that had a height of 1, and so it's really 1 plus x. And so the part that actually is the triangle is just x. Sorry, I feel like that wasn't super clear, but hopefully the other explanation did the trick. So we have an isosceles right triangle, and so both of these sides have to be x. And so what's the area of this triangle going to be? It's going to be x times x, or x squared, over 2. And so the general formula is going to be that a of x, and I'll write down the actual original integral first again. So it was the integral from 0 to x of t plus 1 dt. And what's our area formula we just came up with? Well, it's x squared over 2 plus x. So I'm just going to put a box around this. So again, in tomorrow's video, in the next video, we're going to be basically seeing like why, what the significance is of this. I mean, if you want, you can start thinking about it. Maybe look, my hint to you would be to look at this function in here and look at this function out here and see if you can notice any kind of connection between them. And then do the same thing for this previous example. So function in here was 3, function out here was 3x. See if you can notice what the connection is. And then in today's worksheet, I'm going to basically have you do kind of a variation on this problem where I'm going to change the lower bound to be a different number and have you kind of repeat this process. So I really, really would appreciate if you do the worksheet that goes with this video, just because I'll kind of be running tomorrow's video under the assumption that you did the video for this video, or sorry, that you did the worksheet for this video. All right, that's it. So we will get into the fundamental theorem of calculus tomorrow, and yeah, I'll see you then.